In the previous videos, we've looked at how to use node voltage method to determine an equation for a circuit. In this video, we're going to look at how we can generalize that method so you don't necessarily have to know the underlying circuit analysis so much, but for most cases you can just come and plug into this equation. So up at the top here, I've got our definition for an essential node again. So remember, our essential node is just a node where we have 3 or more elements connected. So by elements, I mean things like resistors, capacitors, voltage, current sources, any of those count as elements. And so again, here we're looking at generalized equations. So oftentimes we're going to just have 1 or 2 of these lines, but I've just tried to keep things as general as possible so that you can always pull from this. But I want to point out a few things so that you can use this appropriately. And in the next video, we're going to look at an example. So the first thing to note is here I have sort of a very general case for n+1 essential nodes. So for example, in the previous video, we just had 2 essential nodes, which meant that we had 1 equation. So over here, if we come down here and look at our equations, of course I have this sort of ... here, but let's say this would be our first equation, this would be our second equation, so on and so forth, all the way down to our equation n sub e minus 1, where n sub e is equal to the number of essential nodes. So going back to that example in the previous video, we said we had 2 essential nodes, so that means we're going all the way up to 2 minus 1, which is just one single equation as we saw in the previous video. In our example in the next video, we're going to see we have 2 essential nodes, 3 essential nodes, so we're going to have 3 minus 1, which means we're only going to have 2 equations. But again, I've kept things very general here so that you can kind of scale this up as needed. So let's take a look at this first equation here, and I'm going to point out a few sort of trends as we look at some of the other ones. So let me sort of zoom in on this term here so we can see it a little better. So note we have sum of admittances connected to node 1, all of that times V1. So note that we're talking about admittances, not impedances. So remember, we had defined admittances as the inverse of impedance. So just to write that here explicitly, we had said that our admittance Y is equal to 1 over our impedance G, our 1 over our impedance Z. So we're summing the admittances that touch node 1, and then we're multiplying all of that by V1. We're then subtracting any admittances. So again, we're dealing with admittances, and if we kind of look ahead, we see we're dealing with admittances in every term here. We're subtracting any admittances that are common to nodes 1 and node 2. So that means anything that connects node 1 and node 2. And again, we'll see this a little more clearly in the example. All of that is multiplied by V2. So we keep on subtracting, so on and so forth. And again, we're summing all admittances. Now if we're looking at node n, we're looking at any admittances connected between node 1 and node n, and that's being multiplied by V sub n. So we have all of that, and we set that equal to the sum of the applied currents. So note we have to have applied currents at some node. If we have voltage sources in our circuit, we can't account for it with this generalized equation, and I'm going to come back and talk about a couple techniques to get around that in a later video. Okay, so sort of zooming out here again and looking at that holistically, what we see is all of these terms on the left side of our equation were negative except for 1. The only term that is not negative was the term with our V1. So our equation 1 is going to have a positive term multiplied by V1. Now if we go down and look at the second equation, we note that the same sort of trend is true. So for our equation 2, the only term that's going to be positive is our term that's multiplied by V2. So let me erase that. That kind of looks like a plus or minus. So our only positive term is the 1 being multiplied by V2. All of the other terms are negative. So all of these are negative. Again, just like with the previous one, we're dealing with admittances. So everything over here on the left side is admittances. For our term 2, if we're looking right here, we see that it's sum of admittances just connected to node 2. For every other one, it's going to be sum of admittances between that node and node 2. So for example, our V1 term, we're looking at admittances connected between 2 and 1. And then again, on the right side, we're looking at applied currents at node 2. And so similar thing, we just keep on going down. For this last equation, if we were looking at some system with n plus 1 essential nodes, now, of course, we're still looking at admittances in each term, and we're looking at node capital N. So we're looking for our Vn term as the only positive one. That's all the admittances connected to node N. And then for all the other terms, it's admittances between that node and node N. So for example, here is 2. So for multiplying by V2, it's admittances between node 2 and node N. And once more, we see it's applied currents at node N. So hopefully that gives you a little bit of an idea, but I think it'll be a lot easier to grasp in our next video when we look at how we can use these equations to solve a circuit. And then, as I mentioned, we're going to come back and I'm going to just mention a couple other circuit analysis techniques that can kind of help us get around when we don't have our circuit ready to put directly into this equation.